Let's say we know the velocity of some particle is given by this function 20t minus 5t squared when evaluated with time in seconds will give us units of meters per second coming out. And we want to know what's the functional form for the acceleration. So functional form means we want to know what's my acceleration as a function of time. So I want a equals something that might have t in it. Well, we can start off by plotting this. We have velocity as a function of time. It's got a t squared in there, so you might expect a parabolic relationship. It's got a negative there, so it's probably upside down. And indeed, that's what we get. So velocity is a function of time. You can see how that behaves. Now I want acceleration. So I could try and split this up into regions and get averages, but since this is continuously changing, it makes more sense to use calculus to do this. So we'll say that my acceleration is equal to dv dt, which is the time derivative of this function 20t minus 5t squared. Evaluating this, the first term becomes 20 times t to the 0, which is just 20. Again, using the power rule, you multiply by 1, subtract 1 from the exponent, you get 20 from the first term. And then this minus 5t squared, when you take the derivative with respect to time, becomes negative 10t. So my function is 20 minus 10t, and the units that you should get out, since we've taken a derivative with respect to time, that's dividing by a time. So we'll have from meters per second, initially, we end up with meters per second squared as my units coming out of that function. We can now plot this, and this looks like a straight line function. So we start at some positive value of 20, and then my acceleration continuously decreases at a constant rate throughout this time interval. Lovely. What if I want to know the instantaneous velocity now at various different points in time? We can take our functional form here and evaluate it for time equals 1 second by plugging in 1 second there. So you plug in 1 second, evaluate it, and we get a certain value. And we'll note that's the same thing that we get when we read off this plot at time equals 1 second. Here, we're at 15 meters per second. So you might expect when you evaluate that function from this plot, like you should get 20, and indeed you do. And then at time equals 3 seconds, you get 15 again, exactly as expected. What about now if we want to find the instantaneous acceleration at those times? Well, we can evaluate this function here that we found for time equals 1, 2, and 3, or read it off this plot that we've made of it already. So evaluating it, you get 10, 0, and negative 10, as you'd expect.